Hey everybody, today we're going to talk about what is inside this earth that's underneath our feet. You can see a graphic here that kind of breaks down the different layers of the earth that we're going to learn about today. And when we're done, you should understand exactly what each of those layers is and a little bit about what it might be like deep down there in the earth. Now, how do we know what's inside the earth? Because really, nobody's ever been able to go down there and take a look around. It's a little over 6,000 kilometers to the center of the earth. That's about 4,000 miles. And we have only been able to barely scratch the surface of the earth. The deepest mine that we have, it's only about 3 to 4 kilometers, about 2.5 miles deep. And the deepest well, the deepest thing we've been able to drill into the earth is only about 12 kilometers. 12 kilometers out of over 6,000 kilometers. We've barely been able to learn anything from just seeing, observing, because we can't really get down there. Now, why can't we? Mostly because of the heat and the incredibly high pressure. At about 12 kilometers down, which is about as far down as we've gone, the earth is hot enough to melt the steel that we're using to make up our drill bits. And so if your drill is melting underneath you, you can't keep drilling. At about 100 kilometers down, the rock is hot enough and it's under enough pressure that even though it's still a solid, the rock it's kind of stretchy and bendy. It's kind of like Laffy Taffy, where, if you hold on to the Laffy Taffy, you gently kind of pull, you can pull and stretch it, even though it's still really kind of like a solid. So we can't actually go down to the center of the earth, despite the cool movies that kind of take us on that trip. So how do we know exactly what is underneath us? It's actually in so many ways a lot more easy to go and observe the surface of Pluto, than it is for us to actually understand and observe the earth beneath our feet. Now, luckily, we do have something that helps us see into the earth. And it's kind of like, you can sort of think of it as an X-ray for the earth. When you go, maybe you hurt your leg or something at a sports practice and you go to the ER and you get an X-ray. They take X-ray waves and they shoot those X-ray waves, those light waves, through your body onto film, and we are able to see inside your body. We're able to see what your bones look like. And the same is kind of true of the earth. We can actually use the different earthquake waves, the waves that are created when there is an earthquake anywhere on the earth, to sort of look inside the earth and to see what it looks like in there. It's not the same as looking, directly at it, but we can still see the inside structure of the earth from the seismic waves in the same way that we can see the structure of your bone, whether your bone is broken or not, from an X-ray at the hospital. Here's how that kind of works. There are 2 types of seismic waves. There's actually more than this, but 2 types for our purposes that we're going to talk about today. There's something called P waves, and P waves are called primary waves. They're able to travel through solids and through liquids. So P waves can kind of travel through everything. Then there's something called S waves. These are secondary waves. They are only able to travel through solids. So if they hit something in the earth that's liquid, the S waves will just stop. The P waves will continue to go on through. And so we're able to kind of use the patterns of P waves and S waves to kind of figure out where and whether there are parts of the inside of the earth that are solid and liquid. That helps us a lot. It's even a little more detailed than that, though. Seismic waves, like light waves, like any kind of wave, Seismic waves will bend, or we call it refracting. They will refract or bend or reflect whenever they hit a new material that has a new composition chemically, that has a different density, meaning it's more dense or less dense, and that will cause the waves to actually bend. And you can see here a model of the inside of the Earth, and it shows you how some of the different P and S waves will start and stop and also bend or refract as they hit different layers of the Earth. And those layers are different from one another. They're made up of different stuff. They have a different chemical composition, and they have different density. And some of them have different states of matter. We have a combination of solid and liquid, or kind of a slushy. In other places, we believe that entire layers, like the inner core, are solid, and other entire layers, like the outer core, are liquid. And so we'll talk a little more about that in a moment. You can see here a few things. You can see that we have the different waves that are kind of bending every time they hit a layer that's a little bit different. There where I just drew that green, you'll notice that the P waves keep moving on through, although they get bent a little bit, but the S waves stop. That's how we know that that outer core area, which is kind of this light, I'm putting a star there, that kind of light yellowish color, that's how we know that that must be liquid, because the minute the S waves hit that, they stop. The P waves, though, come on through, but the P waves get kind of bent, and this creates some areas that we call shadow zones. So we use the combination of how the P waves and the S waves look as we pick them up at different places around the surface of the Earth, because that tells us what's happening to the waves inside the Earth, and that tells us how the Earth is structured, or what's down there. And we're able to create a really good model of what the inside of the Earth looks like. Now, I said about shadow zones. Let me just show you that in a little more detail. In the first picture here, on the left-hand side, you'll notice that there is what's called an S-wave shadow zone that covers much of the bottom of planet Earth here. And the idea is, if there is an earthquake right here at what looks like it would be the North Pole, then those S waves travel through the Earth, but as soon as they hit this feature right there, all the S waves disappear, they stop. And that means that this must be a liquid. And this area on the other side of that, where we don't get any of the S waves from that earthquake, this is the shadow zone. It's our evidence that we do, in fact, have some sort of liquid layer toward the center of the Earth. There are also P-wave shadow zones, if you look over here on the right. And these are not because of changes in state in the Earth, like from solids and liquids and stuff. These are actually from changes in composition that cause the P waves to bend. And they bend in such a way that there are a few of these shadow zones sort of on the opposite side of the Earth from where the earthquake is, again at the North Pole, where we can't pick up directly those P waves. And so we need data from lots of different locations on Earth to figure out where an earthquake happened, to figure out exactly what's happening inside the Earth with those earthquake waves. But a shadow zone is just an area that does not receive the direct earthquake waves, either S waves or P waves, or both, based on this internal structure of the Earth, stopping those waves or bending those waves away from the area that we're looking at. All of this together allows us to create a pretty good model of the center of the Earth. Now, What that model tells us is that we really have 3 to 4 layers of the earth, depending on how you want to talk about them. At the center of the earth, we have a core. And the core of the earth, there is an inner core that we believe is solid. And there is that outer core right here that we believe is liquid. And that's because of the very large S-wave shadow zone that shows up when we have earthquake waves that we're able to analyze. On the outside of the core, the inner and outer core, we have a middle layer to the earth, and this is called the mantle. Think M&M, middle is mantle. And then just at the very surface, this is such a tiny, skinny little layer. It's almost like the scum on a pond, like where it's just barely there, or an oil stain on the top of a little pond, where it's just barely there. To us, it seems large, but on the scale of the planet, it's super thin. We call that the crust. It's the outer layer of the earth. We spend our entire lives on the earth's crust, and to us, it seems immense. It's got mountains, it's got valleys, it's got all of the earth as we see it and understand and know it. And yet, in terms of the amount of rock and the size of the planet, it's only a tiny little skin or layer on the outside. We're going to take a little field trip through each of these layers and just talk a little bit about what they're like and see if we can't build ourselves a better understanding of what the earth beneath your feet is doing. Now, let's start at the surface right here where we live, and let's talk about the crust. The crust is that thin skin on the outside of the earth. It is very cool, and it's brittle, which is a word that just means it's breakable. It breaks easily. When we have kind of motion in the crust from that breakage, that's what an earthquake is, and we're going to come back and talk more about earthquakes. There's 2 kinds of crust that make up the layer of the Earth's crust. There's the crust that makes up the continents, the land masses that we live on. And then there's the crust that makes up the ocean floors. And these are very different from one another. Continental crust, which makes up the land masses, the continents, is fairly thick. It's 35 to 70 kilometers thick on average. And it's very light. It's got a lot of light-colored minerals, light density minerals. It's rich in aluminum, silicon, remember, is one of the big ingredients in quartz, which is that most common mineral at the surface of the earth. It has low density, which means it's fairly light, and we call it granitic crust because there is a lot of the rock granite involved in the continental crust. Now, there are many other rock types in the continental crust, but granite is a very common one, and it's kind of like the poster child for what continental crust is. Tends to be light in color, tans, pinks. Think about light grays, the colors of the rocks that you see around you every day. Oceanic crust is the crust underneath the oceans, at the bottom of the oceans, making up the seafloor. And it's pretty different. It has a lot more iron and magnesium. It tends to be dark in color, black, greenish black, dark gray. And it's mostly made up of a rock called basalt, so we call it basaltic crust. It's also much thinner than continental crust. It's only about 5 to 10 kilometers thick. And so we'll talk a little more later about the implications of that. But oceanic crust usually is covered by water. There are some places at the surface of the earth where we can go to see it, what it looks like. But most of it is underneath the oceans. It is underwater. It's not anything that any of us are ever going to be able to observe. And we will talk more about how oceanic and continental crust interact with each other later when we really get into plate tectonics. Now, underneath the Earth's crust, there is this middle layer that we call the mantle. This is the thickest layer. It's about 2,900 kilometers thick. It's really thick. It is most of the volume of the planet. About 83% of the planet's volume is in the mantle. It's the big layer. And the rock here is warm to hot, and it is under incredible pressure because it's got the weight of all the rock on top of it pushing down. And so the further you go down into the earth, the more pressure the rock is under. And the combination of the heat and the pressure really makes rock act in ways that we don't normally think of rock acting. For example, the rock is a solid still, but it's more like plasticky. And when we use the word plastic, what we mean is that you're actually able to kind of stretch and bend and move that rock around without breaking it. It's kind of like Laffy Taffy. And the rock can flow, which is a very strange idea because the rock is still a solid, but it can flow very slowly over time. It's not liquid, it's not melted or anything. It's just sort of like taffy. You know, if you think about Laffy Taffy, if you've ever had it, if you want to break it, you hit it like real hard and it'll break into pieces. But if you just take the edges of the Laffy Taffy and just gently pull, it'll kind of stretch out. And the earth will flow and stretch and bend and fold around like that inside of it. What this makes possible is currents deep in the earth where the rock is actually being moved and carried. And a lot of this has to do with heat transfer. We're going to talk about this in class more. And we call these great currents in the mantle convection currents. And these convection currents in the mantle are responsible for a lot of what we experience here at the surface of the earth. Responsible for volcanoes and volcanic eruptions, earthquakes, the presence of mountain ranges, the presence of big valleys, the shape of the continents and the oceans, and we're going to learn about all of that. The convection currents in the mantle, they are the driving force of plate tectonics, which is the topic of this unit that we're going to be learning about. The rocks in the mantle have more iron and magnesium than the crust rocks do. They're more dense, and they have a lot of this greenish stuff. This is a mineral called peridotite. In gemstone quality, this is where peridot comes from. And we actually have some of this mantle rock at the surface of the earth, just to the east of the valley. There are world-class peridot deposits out there. And we'll talk more about that in class 2 a little bit. Now, you can kind of divide the mantle into the lower mantle and the upper mantle. It's mostly based on the temperature and how the rock behaves. The lower mantle is hot, it's super plasticky, it's bendy, it's stretchy. The upper mantle is more brittle, it's more breakable, it acts a little more like the crust does. There may be some slushy areas or a few areas here and there that might be liquid, but on the whole, it's still pretty solid and pretty breakable or brittle. Now finally, we get to the core of the earth. This is what makes up the earth's center. It is incredibly dense. It is extremely hot, up to 6,000 degrees Celsius. To give you some perspective, that's about the temperature of the surface of the sun. So the center of the earth is about as hot as the surface of our star, which is kind of crazy. It's fairly thick, but it is in the center. It doesn't have as much volume as the mantle does. And we break the core down into 2 parts. There is the inner core at the very center of the planet. We believe that this is just solid iron. There are some people that are believing at this point that there might be a single solid crystal of iron down there. But it's it's hard to get information from down there because we can't go visit it. It is the most dense part of the earth, and even though it's so incredibly hot and it's the hottest part of the earth, It's solid due to the high pressure of all the rock pushing down on it. The outer core then is iron, but it has some nickel mixed into it, and we believe that it is liquid because of that S-wave shadow zone. It is less dense than the inner core, but more dense than the mantle. It's super hot, and it has a very special role to play in making life on Earth possible. We believe that currents in that outer core, in that liquidy metal outer core, they are responsible for creating Earth's magnetic field. And that magnetic field makes life possible. And we will talk a little more about why that is in class too. So I am very grateful for the liquid outer core because without it, the surface of the Earth would look a lot more like Mars does. Mars does not have a magnetic field like we do, and that's because Mars, we believe, has frozen solid. And there is no longer any current, metallic currents in their outer core on Mars to create the magnetic field for that planet. So we have these layers. As we go down toward the core, we get hotter, we get higher pressure, we get higher density, we get more metals like iron and magnesium and nickel, the heavy stuff. And here we go. There is another way that scientists will sometimes divide the layers of the mantle and the crust. And it mostly has to do with how the rock of the mantle and the crust behaves, especially when we start to talk about plate tectonics. There are different seismic properties that are shown by kind of different layers. And so there's different ways you can divide things up. The lithosphere includes all of the crust and the solid portion of the uppermost mantle, the part that I said was kind of breakable and acted a lot like the crust. That would be this right here. And that lithosphere is broken into pieces at the surface of the Earth. We call those pieces plates. And we're going to come back and talk about plate tectonics and define it and all of that. But this lithosphere, the entire crust plus a little bit of the uppermost mantle stuck on the bottom of it, that's what's broken up into the plates. And then that whole system of these broken plates of lithosphere sits on top of something called the asthenosphere, big word. And that's a liquid weak layer in the upper mantle. It's maybe some sort of slushy. This is where we're wondering if we have some liquid here and there, although we do believe that that part of the mantle is mostly solid. And the lithosphere kind of floats on it. We're going to talk more about this. This is just an introduction. But I want you to take a look here and notice that we have the asthenosphere here. It's capable of flowing, bending, and then we have the lithosphere floating on top of it. There's another graphic right underneath it. Take just a minute, look at those graphics. The lithosphere is not the same thing as the crust, and we'll use the words at different times as we talk through the rest of this unit. So here's kind of a summary page. You can see on the left-hand side, we have our 3-layer Earth, crust, mantle, core, and we have the inner and outer core marked there. And then on the right-hand side of the graphic, this is more of the differences we see on the seismic waves, where we have our inner core, outer core, our lower mantle, our asthenosphere, which is the upper mantle, then our lithosphere, which is the uppermost mantle, and the entire crust. Just different ways to talk about how the Earth is structured inside based on what we care about. We will spend a lot of time getting to know the Earth a little better. For now, just make sure that you understand what each of the layers contains and how they're different from one another. Hope you're having a great day, and I will see you in class.